my great pleasure to invite Glenn Shafer from Rutgers University in the States to talk on the language of betting as a strategy for statistical and scientific communication. So Glenn, over to you.
Thank you. I'm very honored by this opportunity to talk to the Society about some work that I have, that is really the fruit of a long collaboration, especially with Vladimir Vovk, and which shows how the work we've done on the foundations of probability can be useful in statistics. So I do have slides, which I will share. Let me, I'm going to begin, let's see, there we go. I'm going to begin with something that I didn't really talk about in the paper, but which I think is, might get us into the idea of testing by betting. And because it's a situation where it's hard to see what the alternatives are. What else would you do besides test by betting? And I'm thinking about testing pundits who predict elections or sports events or even weather forecasters that tell us probabilities. I wanted to focus on the example of Nate Silver, whose website 538.com has been quite elections and United States sports events. So here, for example, is on the left of this slide is the graph of his predictions about who would be the Democratic candidate for president this year, which turned out to be Joe Biden, of course. And you can see the gyrations in his predictions. One moment, Sanders was up to 50% and Biden was down to, I don't know, 10%. The next moment, Biden was the candidate. So the question is, what do these, what meaning, what content, what empirical content could this series of predictions have? And one way of asking that question is to say how you could test them. How could you possibly test them? And I think an obvious answer is that you could treat them like you would treat maybe stock market speculation. Every day you could interpret the probabilities as a price at which you could buy or sell. And every day you could decide what to buy at the current prices. The next day you could sell at the prices. You could rebalance your portfolio. You could sell at the next day's prices and buy what you wanted then at that day's prices, and so on. And if you had a way of doing that, if you thought you knew more than the people putting together these predictions, and you could challenge them in this way, and if you started with $1 and turned it into $100 at the end, you would show that, well, they didn't have it right. At least it would be a very, very good argument that they weren't doing it right. That doesn't mean you would have your own predictions. You would just have some suspicion that maybe they were gyrating too much or overconfident about the leader, and you could find a way to bet against that. There's an important point which I might return to in the discussion because it does affect what I'm talking about later. And that is, this only is legitimate or convincing, I would say, this principle that you can discredit a probability forecaster by betting against them is only convincing if you put the money you're going to use on the table at the beginning. And you aren't allowed to bring more money in if you fall behind. You know, if your betting goes against you, you're not allowed to borrow money, take more money out of your pocket, get a line of credit. No, you put the amount of money, everything you're going to use on the table, and you can only make bets that what you have on the table will cover. What you currently have on the table, which means what you first put on minus what you lost plus what you won, what you currently on the table always has to cover your bets. A very important principle. It's implicit in what I'll be saying later, but if you lose sight of it, it's can lead to dangers, which I think sometimes arise actually in finance, certainly arose in for people who were seduced by betting systems in casinos in the 19th century and even since. I'll skip over the next slides. Let me quickly turn to betting for statisticians, testing by betting for statisticians. What I have to say first there is very, and I'm only covering the basic ideas in this paper. I know that most of the audience and certainly the discussants have read the whole paper, so, but I thought the appropriate thing to do here in my 35 minutes would be to talk about the basics. Of course, the first thing is to define a p-value, or rather a standard significance test, Neyman-Pearson significance test, if you will. The way you would test somebody claiming that a certain probability distribution describes a phenomenon is you would choose a significance level, then choose a rejection region that has that probability, and then reject if the observation falls in the rejection region. This slide is just to introduce the notation I'm using for that. I assume everyone in the audience is familiar with the idea. So this can be given a betting interpretation, which I think is really implicit in a lot of people's thinking, but you seldom see it spelled out in a textbook. The betting interpretation is that when you say the significance level is 5%, the idea is well, you could say you're putting a penny, 5 cents on the table and trying to win a pound. Or you could say you're putting a pound on the table and trying to win 20 pounds. So if you put a pound on the table, then if this rejection region happens, you get back $20. If it doesn't happen, you don't get back anything, you get back zero. If you get back the $20, you can say, well, you've multiplied the money you risk by a large factor. That's sort of the basic principle in this testing by betting. That if you multiply your money by a large factor, you've shown the odds aren't very, maybe they aren't true. So you've discredited those odds. You've discredited the claim that P describes the random variable. And for the public, I think, and even for scientists, it'd be natural to say that's the best evidence you could have. Maybe statisticians and mathematicians, we've trained ourselves to think differently, but I think for the public and for people new to our field, this is very convincing. It's like what else would you do? So we've looked at the idea of a significance test with a fixed significance level, but then of course we have the idea of a p-value, and the definition of p-value is again very familiar to statisticians. And those of us who work for our whole careers with it, it's very natural, simple, but in fact, it's rather complicated. First, you have a test statistic, usually. I mean, you can define the notion of a p-value more abstractly, but traditionally, it starts with a test statistic. That's where the idea comes from. Or in fact, it comes from confidence. It comes from confidence intervals that were introduced by Laplace and Fourier and Cournot in the 19th century. That's where you get p-values, but implicitly there's a test statistic there, the distance from the estimate. So you have a test statistic, and then you have a family of tests, one for each significance level. And the p-value is the smallest significance level for which the test rejects. And then you say, well, the smaller the p-value, the more evidence against the hypothesis. And in red here, I make my main point, which is this is just too complicated. Yes, it's simple for us, but for anybody who's taught this subject knows that it's very confusing. I've talked even with journalists who specialize in covering science who tell me that every time they encounter it, they get confused. So what is the alternative to this p-value? And the betting alternative is to make a bet. Let me get a better look at my own slides here. A bet is a non-negative payoff. So instead of making a bet that pays, 0 or 20, we could make a bet that might pay all kinds of amounts. But I should have said here, or maybe when I say a bet is a function of the outcome y, I want it to be a non-negative outcome. So that's the idea that only the money we pay upfront is going to be what we risk. We don't risk the payoff itself being negative. And it's convenient to choose this payoff so that its expected value is 1. So then we're saying we're paying $1 to get back some non-negative amount, S pounds. Did I say $1 or did I say £1? We pay £1 to get back S pounds. And then we say the more money we made, the more evidence we have against P. So I want to call this amount that we win when we invest $1, the betting score. The higher the betting score, the more evidence against the hypothesis. It's the factor by which we multiplied your, by which you have multiplied your money. And I assumed, I made this assumption here that the expected value of the payoff is 1. We paid 1. But that's not really crucial. We could pay a different amount, and then the betting score would be the ratio of what we get back to what we paid. That's unchanged when we multiply S by a constant, so we could always multiply it by a constant to make the expected value 1. Immediately, as I explain in the paper, a sort of obvious fact that is seldom talked about, and in fact, I've found, I haven't been able to find anybody that's talked about it, is that the betting score, and defined in this way, is actually a likelihood ratio. So what I've just told you is that a bet, S, maybe I've used this word, a bet. So we have the difference between a bet and a betting score. The bet is a function. It's the payoff you choose when its value is not known yet, and the betting score is the actual value that you turn out to get. So the bet is a function of the outcome y that's non-negative and has expected value 1, which means that if we assume discreteness to keep our ideas clear and simple, the expected value is to get that, you multiply the probability of each outcome times the payoff when that's the outcome, and add those up. That's got to be 1. When you do that, when you write that equation down, you see immediately that the function of little y of S times P, that function, the function S times P, is also a probability distribution because it's non-negative. Its values are non-negative and add to 1. So let's call that probability distribution Q and call it an alternative. And once we've done that, we've written Q is equal to S times P, then we can divide both sides by P, and we see that the betting score S of Y is actually a likelihood ratio. So a bet against P defines an alternative distribution, and the betting score that we get from that bet is the likelihood ratio formed by dividing the probability given by the alternative to the outcome by the probability given by the null hypothesis. Conversely, if you start with an alternative Q, Q over P is a bet. That's a simple bit of algebra, which I put in the box there. So basically, the idea of a likelihood ratio and the idea of a bet look like the same thing. But that's a bit of a sleight of hand here. If you really took this alternative Q seriously, if instead of starting with the bet, instead you started with Q. So you have a null hypothesis P and you say, this Q is what I want to test against. If that was your situation, would you want to use the likelihood ratio as your test? It's not what Neyman and Pearson said to do. Neyman and Pearson said to use the rejection region for which that likelihood ratio has the highest values, not to use the bet that is actually the likelihood ratio itself. So why would you do that? Why would you use the likelihood ratio as your bet if you want to test against Q? And that leads us right to the idea of multiple testing, because multiple testing is the motivation for using this likelihood ratio as a bet when you start with the alternative. And we see that from Gibbs inequality. So Gibbs inequality tells us, that's in the box up here, it tells us that if you put any R, use any R, the expected value of the logarithm under the alternative of your betting score, if you use R over P instead of Q over P as your bet, the expected value of the logarithm of your betting score under the alternative is less than if you use Q over P, that likelihood ratio as your bet. So that particular bet maximizes the expected value of the logarithm of your score under Q. That's right there at the top. Why would you want to maximize the logarithm of your score, the expected value of the logarithm? Why not maximize, as I say, why not maximize the expected value of the score itself? Or why not maximize the probability under the alternative that the score is bigger than some number like 20? This is what Neyman and Pearson told you to do. That's what their Neyman and Pearson lemma is about, how to maximize this quantity. So instead, we're saying we're maximizing this quantity. That's what we're doing when we use Q over P as our bet. So the reason for using that is if you want to if you're going to do another test. So we're looking at testing for science. We're not looking at quality control, as Fisher said. Here we're taking seriously Fisher's criticism of Neyman Pearson. Fisher said that's fine for quality control. But that was kind of a debating point for him. But let's take it seriously. Let's say that, okay, we're going to use Neyman Pearson for quality control, for decision making, when that's our point, is to make a decision right now. And there's plenty of situations for which that is what you want to do. So we're not throwing Neyman Pearson and the Neyman Pearson lemma out. We're not getting rid of it. We're saying, okay, we have two different situations. One situation is where we have to make a decision, where we were testing widgets, or we're screening a zillion hypotheses, and we want to know which 20 of them we're going to use and look at more closely. If we're doing some screening kind of thing, or some quality control thing where if we throw it out, it's thrown out, we don't look at it again. That's one situation. That's the Neyman Pearson situation. But the Fisherian situation is where we really are doing science. And this test is not the last test we're going to do, or somebody's going to do. We're looking at a hypothesis that a lot of people, a scientific hypothesis that people are concerned about. So, our word is not the last word. This is one test, but there should be further tests. So, and when we make those further tests, I'll argue that we'll want to multiply the betting scores. And if you accept that, if you say, okay, we're going to multiply the betting scores, then that leads to wanting to maximize the logarithm, because as John Kelly Jr. said in 1956, when S is the product of successive factors, the expected value's logarithm measures the rate of growth of S. So if you This has been used in gambling theory, this idea. It's been used in finance, been used in information theory and machine learning, but it hasn't really been used directly, this idea that I know about, in multiple testing and meta-analysis. And that is the proposal here. Now, when I write Gibbs inequality, I remind probably most statisticians of Kullback-Leibler distance. And so some of my correspondents have reacted to this by saying, oh, you're using Kullback-Leibler distance. No, I'm just using Gibbs inequality. The motivation here is not information theory. The motivation is not Kullback-Leibler. So why should we do successive tests of, why should we multiply when we're doing successive tests? Let me give of course, I'm only on page 16 of 30 slides here. Let me think about what I'm doing. I better speed up a bit. Maybe you've seen this argument in my paper. The idea is that if you multiply mediocre, if you were to average your betting scores, that would be a betting score when you average them, then you average 2 mediocre scores, you get another mediocre score. But if you multiply betting scores, if one betting score is, oh, you've taken $1 and turned it into $1.50, and the next betting score is the same thing, you've taken $1 and turned it into $1.50. Well, if you multiply, if you say, on the second time, I'm not just investing $1, I'm investing the $1.50 I had from the first go, then you've got up to $2.25, or excuse me, £2.25. So the multiplication is more powerful. And so we want to aim for large products rather than large averages in when we're testing, we're focused on testing a single scientific hypothesis. So that's the idea. Now, this leads to the notion of implied target. If you're using Q and you're trying to maximize the logarithm of S, then this expected value is what you're aiming for. So if your test doesn't have, so this tells you, this says, what's this test worth? What's it trying to do? And if it's aiming for something that's not very big, then it's not a very good test. So, so the idea is that we could evaluate tests before we even do them, not using power, but using this implied target. So we could propose a test that has, okay, we're going to use Y to test P. S is going to be our test that implies an alternative Q. And that tells us what the implied target is. We could send this, if we wanted to do pre-registration, we could send this to the editor of the journal in advance. And of course, if the implied target is just 1.2, well, that's not going to accomplish much. But if the implied target is 5 or 10, then, and you can take this implied alternative seriously, then okay, it should be a good test. This could be a good study. Maybe we could agree to publish it provisionally, conditionally, even before the study is done. And that might make pre-registration a more rewarding and practical thing to do. I think that's a major contribution this idea could make, one major contribution this idea could make. Of course, you know, you could say, well, I don't really take this implied target seriously. It's just implied by my test. But it doesn't matter whether you take it seriously, the editor's going to take it seriously because it's the optimal, it's what your test is optimal for this distribution. So if you don't take seriously the distribution that your test is optimal for, why are you doing that test? So it's, you know, you're kind of forced to take it seriously if that's the test you want to make. And if it's not, you know, so I give examples. Gelman and Carlin have pointed to this kind of situation as the main culprit in the replication crisis. My example one, you've got a, you know, your null hypothesis is got expected value 0 and standard deviation 10, and you actually see result 30. 3 standard deviations from the null hypothesis looks very significant. But the only, you know, the plausible alternative is only 1 unit from the null hypothesis. So something strange has happened. You're practically, there's only a 6% power. you wouldn't want to do this test. And yet people evade saying they manage to do tests like this. And social science, as we all know, social science is full of tests like this. I mean, in psychology, as you know, Gelman and Carlin were saying that it's, you see it all the time in psychology and in social science. In my own department of accounting, it's almost the standard thing to do. I cite an article by William Creedy where he points out that even our prime journal in accounting even defends doing it. It's a scandalous situation. So the need to communicate more clearly what is going on in this situation, I think, is very important. It's a situation where the power and the implied target imply the study is worthless. But if you evade talking about power because you say, oh, I don't really know what the alternative should be considered, people are getting away with that. But with this technology, you can't evade it because the implied target is a consequence of the test you do. The likelihood ratio is going to show the evidence is very slight, and the betting and the likelihood ratio is the betting score. So, you know, the test doesn't produce anything, even though you've got a rejection of the null hypothesis. So I have two other examples, but I think I have, and you know, one example is where you have a borderline outcome. And this example brings out the confusion that, you know, it's maybe not as common as, it's not as common a situation as example one, but it's also an element, one of the elements of confusion in teaching statistics the way we do it, that because there's a conflict here between the idea of significance testing with a fixed level and the idea of a p-value. And that really comes out in this example. You've got a high implied target and a high power, and looks like a great test from the Neyman Pearson point of view. When you're looking at fixed significance levels, which power does, but then the p-value and the likelihood ratio are strongly in disagreement, and the likelihood ratio is giving you the answer that statisticians would intuitively use. So this is a situation where the statistician has to resort to some sort of likelihood ratio argument or some kind of Bayesian argument to contradict what they first teach their students, what we first teach our students about p-values and significance tests. So it leads to a very confusing situation. If we weren't teaching p-values, if we were teaching betting scores instead, we wouldn't run into this mess. Then the third situation is the high p-value interpreted as evidence for the null, which maybe I was confused on example one. This is a situation that we most often see in a lot of stuff in accounting that I was complaining about first. So I won't say much about warranties, except there is, you know, confidence intervals do emerge in this situation, but we interpret them a little differently. A confidence interval is basically the set for which we would make a certain amount of money. So, you know, these warranty sets really are confidence intervals. They have the same they have the same failures, the same disadvantages of confidence intervals. I just wanted to conclude with a glimpse of the game theoretic foundations for probability that lie behind this notion of testing by betting. I'll remind you of Markov's inequality. The idea that you're not going to multiply your money by a large factor would be, I think, for most of us, the way we would first understand this is using Markov's inequality. The probability that you start with $1, that you pay $1 for a non-negative random variable, namely as if that's the expected value that you pay, the probability of coming out with C times that is less than or equal to 1 over C. That's what Markov proved in 1900. So Markov's inequality gives us some intuition that if you think an event of small probability is not going to happen, which is the intuition behind significance testing, then you think you're not going to multiply your capital by a large factor. So game theory probability basically turns that around. That says, where's this idea that an event of small probability is not going to happen? It's much more for people not schooled in probability, if they just start with knowing something about betting, the idea that you're not going to multiply the money you risk by a large factor is much more, is a starting point. You could have that idea, you could understand that before, probability theory was not invented until mathematical probability theory was not invented, until a few centuries ago, but people understood betting long before that. So it's a much more fundamental and enracinated, rooted idea that you shouldn't be able to multiply your money by a large factor if the odds are accurate, if the odds really reflect what's going on in the world. John Veal in 1939 generalized Markov's inequality by to the situation where you are allowed to continue betting, optional stopping, some people call it, or optional continuation. That was already formulated by Veal, and the idea of game theory probability, when you really turn things on your head and take this notion that you're not going to multiply your money by a large factor, even if you are allowed to continue betting, when you take that as the fundamental idea you're starting with, then Veal's inequality turns out to almost be a definition. That's a first look at the contents of the paper, and I want to thank you again for this opportunity to talk about it to the Royal Statistical Society. Thank you.
Thank you very much, Glenn. That was presented beautifully clearly. Some of the audience were pointing out that they were hearing some fluctuations in sound, and I think it was as you were flipping slides, the sound was dipping and back again, so there may be a technical issue, but your actual presentations and slides were fine. So we're now going to combine one of the oldest traditions of these kind of discussion meetings, which is the vote of thanks, but doing it in this very kind of new tech way on Zoom. So I'm going to call upon Phillip Dawid from Cambridge University to propose the vote of thanks. Over to you, Phil.
Well, thank you very much. And thank you, Glenn, for a fascinating paper, very interesting presentation. I've been following your work, as you know, for many decades now, always found something new and stimulating. And this is no exception. And I really like the idea of making bets fundamental. And I tend to go along with what you say, that it may well be easier for the general public to take this approach and to understand than it would be for statisticians and scientists. I mean, we have been really diverted into strange ways of thinking. And like the Red Queen, we've been taught to believe 6 impossible things before breakfast in the way we apply a lot of statistical tests. Betting is natural, I think, to many people, but maybe not to the people who are going to matter and that you're aiming at, which is a pity. In this context, I'd just like to mention a very nice book I discovered recently by a lady called Annie Duke. She is a master professional poker player, and she has written a lovely book called Thinking in Bets, in which she explains how you can take the ways of thinking when you play poker and use them for making your life decisions. So let's start thinking in bets. And I do hope, I really do, that scientists and statisticians will start thinking of bets. Alas, I feel it may be something of an uphill struggle. So what's really new in what Glenn has said? We have the new principal idea, which is instead of the all or nothing bet, which is implicit in significance in a significance test with this rejection region, we have a much more nuanced payoff function. So that's the first thing. The other important point, again, very much unlike what we have when we're thinking about general Neyman-Pearson tests, is that it's just the value of the bet that we finally get, the value of the payoff, which matters. We don't care about what might have happened. The evidential import is just in how much we managed to multiply our stake by, not what it might have been. That we can consider beforehand and when we're thinking about implied alternatives. But when the data are in, it's only the actual bet, the payoff that we've received, which counts as the evidence. There's I think there's a great idea there. It's not a new idea in the sense that if you believe in likelihood inference, you'd think much the same, and it's only the value of the likelihood function. And indeed, as Glenn has shown, there are many connections between bets and likelihood ratios. There's a lot in the paper which Glenn didn't have time to talk about. He mentioned some comparisons with the Neyman-Pearson lemma. He's got an extension of the Neyman-Pearson lemma in the paper, which is very simple and very neat, and I like that a lot. At this point, I'm going to see if I can share my slides with you. Let's hope this is going to work. Okay. So a lot of what Glenn was talking about was to do with testing a single proffered probability distribution for a phenomenon. We talked about how to select the best bet to use. Well, if we have a real meaningful alternative distribution Q, then both in Neyman-Pearson theory and in Glenn's version, we know that the likelihood ratio is something we have to focus on. And it's just the likelihood ratio itself when we're thinking about betting. It's not obvious otherwise what we should do. We might not have a specific alternative. We might have lots of alternatives. And one way of thinking about it is we don't just place one bet, we place a whole lot of bets. There are many, many ways in which we can think of departures from the proffered distribution P. So why not? And if P is really valid, then we shouldn't really be able to clean up on any of them. So if any of those actually does clean up, then that would suggest that that's evidence against P. So maybe I should place a family of bets and just look at the maximum which is obtained. In which case, it's not clear whether that would contain the evidential value without further adjustment, or would it perhaps require some sort of further adjustment as we do in classical statistics with Bonferroni adjustments. And an important question there, if we do have to adjust it, will we then have to think about the way in which the data were generated and lose the simple interpretation that's the actual value that counts rather than how it was generated and what the probability distribution was in which it was generated. So there's a question on that point. Now, there's a reasonably chunky part of Glenn's paper, which is about parametric models. He didn't say very much about it in the talk, but it is really rather crucial to statisticians. And my feeling is that whereas I'm quite happy with the betting story when it comes to testing a single model, I'm not quite so convinced when we're using a parametric family. And one of the reasons is we essentially have to choose a bet for every possible value of the parameter. That's much harder to motivate and it's much harder to execute. Um, Also, what's happened in this more complex environment, but very important one, to the really intuitive and important concepts which we had in the single distribution case of the implied alternative and the target, when we had this whole family of bets. And can we just use a completely unrelated collection of bets, one for each parameter value? It would be like saying in the classical Neyman Pearson approach, okay, we can just test each theta value with a test which is completely unrelated to the test we use for any other theta value. There's a lot of theory which says how we should do tests, things like uniformly most powerful tests. That ties together how we do the test for different parameter values. Can we do something similar in this context? And as an illustration of that, I'm going to think about something which, again, Glenn didn't have time to talk about, but he moves to, he has a particular example, which is protocol 7. And I've reformulated it slightly. If you look in the paper, it's I'm not quite sure what page it's on. But, yes, it's on page 21 of the paper, and that's been reformulated slightly. There's a family of well, let's call them distributions. It's a bit more subtle than that, but they're parameterized by a mean parameter mu, and there's a story there, and that builds on a protocol which we had for a single distribution. And he talks in the paper about a particular strategy you might use when you have just one distribution P, which is a bit simpler than that protocol. That's protocol 6. It doesn't involve mu. So he talks about a strategy, and any such strategy, it's actually a sequential story. So at time n, you would choose some value an, which you can specify some function of previous information you've got, E1 up to En minus 1. So you specify, the strategy is specified by these functions phi n, and when you've got the an, you just put it in here. This is your instantaneous payoff, and this is your cumulative payoff. And the point about this is that according to this strategy for the more complicated case with mu, that it says exactly how an should depend on the data, the y's, and the parameter mu. And the important point is that the identical functions phi n are used no matter what mu may be. So that is to say, we have a way of tying together the different betting functions, these are the instantaneous betting functions, for different values of the parameter mu. And that seems like a nice thing to do. And it's clear that there's a sort of simple location structure here, which we've used, and we could extend it to problems with group structure. And I'd like to know, is there any general theory that we can bring in, just as we have things like uniformly most powerful testing in classical theory, which would tie these together in a more integrated fashion. We need some guidance, I think, on this. Okay. And finally, one thing which is really, really nice about this whole approach is the way, without any adjustment, we can do optional stopping and optional continuation in really rather precisely or vaguely specified sequential problems. That's really, really nice. It's very straightforward. It gets around a lot of problems that we would normally have. But there is a wrinkle on this, which is sometimes what we get to see isn't all the data that were generated. So for example, suppose that there was a random walk with an unknown upward drift, and it was to be observed, say, for, we know it was going to be observed for 100 steps, but the data which we actually get to learn is the random walk up to the time that it reaches its maximum. So we know there's data which we have missed, and if we were doing likelihood inference, then there is actually a way of correcting for the missing data, a correction factor. There's a face value likelihood, which is ignoring the fact that we've got missing data, but we'd have to apply a correction factor. And I'm just wondering whether Glenn has a way of extending this idea into the betting framework. So that's all I have to say, except to once again thank Glenn for a very stimulating talk, following on the wonderful work he's done over so long. And only to say that I hope you will all join me virtually, remotely, but very loudly in joining me when I propose a vote of thanks to him.
Thank you, Phil, but not yet, because the vote of thanks has been proposed, but not seconded. So to thank Phil for what he said, and we are now again in time-honoured tradition going across to Frank Coolen from Durham University to second the vote of thanks. So Frank, over to you.
Thank you very much. I hope you can all hear me. Thanks first to Deborah and the Royal Statistical Society for inviting me to contribute to the discussion. Indeed, it's a very, very interesting paper. Like so much of the work of Glenn, I actually learned things from it. It's not always happening, but it did. I particularly like that the uncertainty is explicitly quantified on observables or simple functions of observables. It always makes life easier, I think. There's no doubt that the betting interpretation is particularly useful in sequences of bets. If you have situations where you have multiple experts and you want to get a feeling of their level of expertise, let them bet, and the one who has most money at the end is probably the best expert. In this paper, I particularly like the betting score as a likely ratio between the Q and the P, the implied target, very beautiful. And I also think that for the many situations in practice where people are doing a single test, the paper does provide an argument in favor of the Nyman-Pearson scenario, maximizing the probability that the betting score exceeds a certain value under the Q distribution. To me, that still seems quite attractive for the single test situation, which I think in practice is what many people still do. I don't have any real contributions. The time I had with the holiday in between was not that large, but reading the paper, I have a few questions which perhaps could point towards new further investigations. The starting point that I had was by looking at the random quantity y. It seems very easy to say, well, there's a random quantity y and there's a probability distribution for it, and that's the starting point. Many tests in practice do not work like that. People may have two treatments and they want to see that the one treatment is better than the other treatment. And that doesn't necessarily directly relate to having a y in a distribution. We have classical theory where then test statistics may be recommended and an asymptotic distribution for that, or non-parametric combinatorial distribution, and then it is applied. But I don't necessarily see how that will always lead to the current setting in a way that is easy to implement for people who are not experts in statistics. And that was the main thing of the paper, that the idea is that the methodology will be easier for people who are not experts in statistics. I'll come back to that later. If we have a real valued random quantity of interest, then eliciting a meaningful probability distribution, P, and also Q, can actually be pretty hard. And the betting rate can be quite sensitive, I think, to relatively minor differences in such distributions. So how we would implement that in practice may perhaps be a bit tricky also, or particularly for people who are not experts in statistics. Of course, we can only know how it will work by doing it. Another observation I have is that we do need to know why. And to formulate the P and the Q meaningfully, we do need to know, therefore, I think, aspects of the data collection process, the design of the experiment even. So I'm not entirely sure to what extent we can say that such aspects are not important. It is good to know the experiment in order to meaningfully assess the probability distributions involved and why and the values it can take itself. I was thinking about the question, who chooses why? Okay, if we have a situation, and this is close to the beautiful example 4 in the paper, which unfortunately Dan had no time to discuss, is example about Fisher's analysis of Weldon's dice data. You can look at the data in several ways and you can come to different conclusions. And I was thinking if we have a very simple example, but we have a sample, y1 to yn, and the feeling is that these come from a standard normal distribution, IRD. And the alternative Q could be that, yes, it comes from a distribution with mean 0, but it has more variation. So standard deviation, say 3. Now, we can see this as a sequence of n bets, a bet on each of the observations, or a bet on a sample statistic, a sufficient statistic, say the mean. And these can, of course, give very different results. If n is 2, and if we have the observations somewhere in the order of y1, somewhere in the order of -3, and the other y2 of +3, the mean is 0. So the P distribution will be winning in terms of the betting. If we do it sequentially on the 2 individual observations, then the Q would win because the observations are much more likely under Q with a larger variance. And this is nothing to worry about because they are really fundamentally different bets, different events. It's actually quite interesting that if the interest is in a different variance, that you can do a meaningful bet when you would only have the mean value. But my question here would be really, would there be some theory or some arguments in thinking, well, perhaps we should always then do this sequential case if we have these samples? Because if we have sufficient statistics, and if this was a sufficient statistic under P, which is the starting point, then it may not enable a person to specify Q in a meaningful way as an alternative. Even more so that in hypothesis testing, the real target, the thing that one really wants to try to find evidence for, is in the alternative hypothesis. So the question is more, in the practical scenario, who chooses why to go on with this? This is beyond what's in the paper, because in the paper the why is given and it's a beautiful result. But for the implementation, I think it is important. And it will be interesting to see whether this can be looked at. For example, would there be sufficient statistics that are in some way optimal in distinguishing between a P and a Q? So now let me go on to a slightly wider issue, which is also at the start of the paper. It's not so much addressed in great detail, but it is this fact that there are problems with the p-value and the wider issue of problems with implementations of testing reproducibility or so. I sincerely hope that work like this can make contributions. I somehow fear that it gives more insight to the people who have good understanding of mathematical statistics rather than people who want to add some statistics to a detailed study at some of the last hour of their study when the data is there, and then they want to do some black box method. That would never be a good thing to do, of course. My view on this is that statistical inference is hard, that we need the experts for that, and it is really very difficult to find methods that people can use as black box methods and use them correctly and meaningfully. I think one problem with the p-value, and this goes back to the theory and the history of the theory of statistics, of which Glenn, of course, knows so much and has taught us all about, is that not only is the p-value vague to many practitioners what it is as an answer, but also the question it answers is very vague. People in practice normally do not have the question that it is answered by the p-value and by hypothesis testing. So methods where the actual real-world questions, is one method better than the other, or more closely put at the center of statistics and then answered, are favorable, I think, and I'm not sure whether the betting approach can really help with this. I think there are opportunities, but it would be nice to see it. With regard to the reproducibility issue, which is a topic that many people have commented on in recent years, I think that the problems with the p-value may be part of it and the lack of understanding of that. There was a really nice, two papers, one by Goodman and one by Stephen Sen in Statistics in Medicine, 1992 and 2002, where they raised this issue. And they explained that if you have a rejection region, if your test statistic happens to be on the border, on the threshold, then there is probably a probability of about a half that if you would replicate the experiment in exactly the same situation, exchangeability of the observations and so on, that you would get another outcome. And we have recently done quite a bit of work in trying to understand reproducibility purely from the statistical methods point of view, where we say, well, we assume that we are going to do a test again tomorrow, we did it today, with exchangeable random quantities. So the scenario is entirely the same. And we see it as a predictive problem. It turns out then that the reproducibility is really quite low. This idea that it may be a half around the threshold holds, but if your alternative is one-sided or only that method 2 is better than method 1, then it can actually be quite a bit lower than a half. And if you move further away from the threshold, from the border of the rejection region, then still the reproducibility that is implicit to the method can be relatively low. This is particularly worrying in situations where people really want to reject the null hypothesis, because that's the thing that will lead to the new methods to be possibly implemented and so. Reproducibility can be really low there. Add to that the well-known facts that it's difficult to get work published if no new things were shown. And so I'm not entirely sure whether the current method is going to solve that, because whenever people implement testing in the 0-1 decision scenario, and this was also briefly discussed today, but it's an important topic, we keep having the reproducibility problem, I think. The repeat of test, if you're very close to the borderline, is independent of what the p-value really was set. If you would do the test again in exactly the same setting, you would have poor reproducibility. So this is effectively what I want to add. Once more, I truly enjoyed the paper, and also the book with Vladimir Vovk, of course. I recommend everybody to read them. And the only thing that's left to do for me is to formally second the vote of thanks.
Thank you, Frank. Thank you very much indeed, and for keeping, as Phil did, to pretty nice timing. Right, so in time-honoured fashion, the vote has been proposed and seconded. If we were in the old world, we would all now be making a nice noise and clapping. As it is, you need to find the reactions on your screen, and you'll find you're not allowed bad reactions. So there is a clap, which the only other option is a thumbs up. So if you could find that if you can, and show your appreciation. I'm going to make a noise. Right. So thank you very much for proposing seconding the vote of thanks. We now have a list of sort of probably about a dozen people who've indicated that they either want to speak or that they've sent in a written contribution. So I will take them in the order in my briefing notes. And I think that at least for the first 8 who we know are speaking, that their slides have been passed over centrally, so they'll be managed centrally. So the first of those is Harry Crane from Rutgers University. Can I call on Harry to unmute himself, unmask himself, and over to you.
Okay, thanks. Should I share my screen, or is it okay if I share? Okay. Okay. Well, thank you, and thanks to Glenn for the interesting presentation, and I'm glad to have a chance to discuss it, as I've discussed with Glenn a number of times in person, and we've been working together and at Rutgers for several years now. I have no major technical remarks, especially in this short response. I just want to talk a bit about, well, I guess what I see as a promising approach in the game theoretic framework of Vovk and Shafer, but also I'm glad to see that Glenn is bringing this into statistics. What I'll do here is, I know that Glenn is trying to introduce more betting language into statistics, and I'll try to do my part in that regard by bringing some other terminology from gambling into the discussion, which I think is actually helpful for understanding why we see ourselves in a so-called replication crisis these days. It's not because it's too hard to understand the p-value or that we need better communication, but it's because the incentives really aren't properly aligned with the researchers and with the reporting of the research. And I think that betting actually does have a good potential there. So as Glenn and as we all very well know, betting and gambling are central to the historical roots of mathematical probability. But what gets lost in this discussion often is that risk is central to the practice of gambling. If there's no risk, then there's no gamble. And also that there are severe risks, and there's potentially serious, very good benefits, but serious risks posed by the use of statistical analysis for a number of societal problems, whether it be in medicine, in epidemiology, as we're seeing right now, coronavirus, and public policy. But often these risks aren't shared by the statisticians who perform the analysis. And if there is some risk, it's really pales in comparison to the scale of the risk that society has to endure by going along with these recommendations. So to introduce a term from gambling, there's a concept called a free roll, which is a bet that is guaranteed to at least break even in the worst case. So it's a bet where you can win, but you can't lose. And how this relates to science is what I call the free roll effect in science, is that this effect that researchers can benefit, or they get credit when an idea they have works or is a good idea, but they generally face very little or no consequences when their ideas fail, all the while society bears the risk. So where does this leave us? This leaves us in the state of a replication crisis. There are some ill-informed or questionable recommendations in the early days of COVID-19, and maybe even today, and also, as Glenn brought up, election forecasting. So I've discussed this idea a little bit with Glenn, and I think that what Glenn would possibly respond with is that his framework is a way to potentially put hold these people's feet to the fire in terms of challenging their reputations, as Glenn brought up, the weather forecasters or the election forecasters. But I would argue that that's really not enough, that generally reputational risk is cheap because it's just too easy to talk your way out of it after the fact with the benefit of hindsight. And I think that we're seeing some of this in real time now, where a lot of we all had very little information at the beginning of the COVID-19, but a lot of the people who suggested certain things, whether it be the World Health Organization, others such as Cass Sunstein, John Ioannidis, they, I believe, made mistakes at the beginning, but they're still very influential in how we are tackling these challenges and how we're trying to bring this crisis to an end. Or in the case of election forecasting, which is a bit of a lower stakes circumstance, but it's actually a good one to talk about because this is a case where there actually are people betting on this outcome. And if you were to go to the markets, there's actually betting markets that exist. And as of a couple of days ago, those betting markets have Joe Biden in the mid 50% range. Whereas when you look at the 538 or other pundit forecasts, they have Biden at least at 70% and often higher. So there's clearly a disconnect between these markets and between the statistical forecasts. And clearly, if the people who were actually betting real money on this believed those forecasts were worthwhile, they would be betting these numbers up, and the markets would come more into alignment with it. Okay. So the final point that I just want to make is that I think that this is a good start, that testing by betting is the right way to go and the right way to think. But I think that in order to make this language of betting impactful, we also have to stay true to what the language actually means. and to stay true to those principles. And this is what I call the fundamental principle of probability, which is just that a claim, a probabilistic or a statistical claim, is only meaningful if the people who are making those claims actually share in the risk that those claims pass along, whether it be to society or to whoever is affected by it. And I think that if we combine this principle with Glenn's testing by betting, we could mitigate the free roll effect in science. We could make some progress, I really do believe, in the replication crisis. But as Phil Dawid said, I do think it's an uphill battle.
Thank you, Harry, and thank you. I should have said at the beginning that this is a strict 5 minutes, and I will be having to stop people because otherwise we will be running out of time in our discussions, but that was a perfect illustration of how it's done. So Barbara Ossimani from the Polytechnic University of the Marches in Italy.
Okay, so first of all, let me introduce myself and thank you for having me. It's a real honor. I'm not a statistician, I'm a philosopher of science interested in context, ecosystems, where strategic behavior influences the way evidence is collected and also evaluated. So I've always been interested in Glenn Shafer's work. And I find this paper particularly interesting, especially because according to me, its strength is that this testing by betting approach retains as much information as possible in evaluating evidence in support or contra some hypotheses. So I think this is the main strength of this approach. And I have nothing to bet against it. So there is one point I'm intrigued about and that I would like Glenn to elaborate on. I framed it as an objection to align with the discussion scenario, but I'm rather presenting it in order to explore the flexibility of the testing by betting approach in dealing with certain contemporary issues in statistical practice. I'm reading, sorry, pardon me for this, but I think that the shorter the time slot, the higher the probability that you exceed it. So pardon me for this. So I will introduce my questions by presenting a notorious case study used by Andrew Gell-Mann in order to illustrate the role of noise in the current reproducibility crisis. Next slide. Next slide. So in this study, Gell-Mann reports what he calls a design analysis of a study performed in 2012 during the election campaign that saw Mitt Romney fighting against Barack Obama for the US presidency. Next slide. The study found significant results for the combined effect of menstrual stage and marriage status on one's political views. I think most of you already know it, but I'm just rehearsing it for you to introduce my comments. 17%, so there would be a 17% higher chance to be liberal than conservative for single versus married women, or to be less religious and to vote for Obama instead of Romney. However, Gell-Mann's design analysis, which is a sort of counterfactual analysis based on the S and M errors. S stays for sign, so you may make an error that by falling into the opposite side of your true effect, or a magnitude side in the sense of overstating your effect size. Next slide. So the bell curve reproduces the probability distribution of differences between the two groups, married versus single women, that could be hypothetically observed if the effect size were just 2% instead of the presumed 20%. Because of the high variability in the population, the spread of the distribution is rather extended across a set of values of the variable. So within 6 standard deviation, it covers a range which goes from minus 30% to plus 30% difference between the groups. We estimate, Gell-Mann estimates that the true effect size cannot be that large because the related literature and consolidated theory on vote swings has established that vote propensity is pretty stable. Hence, he sets the true effect size at 2% and the standard error at 8.1%, the same of the original study, and then the power comes out to be 6%. With such parameters, the probability of obtaining a significant result on the opposite side of the true direction is as high as 24%. More importantly, if we obtain a significant result on the right direction, we estimate the effect size is much larger than it truly is, at least 16%. That is 8 times higher than it truly is. This, according to Gell-Mann, is a recipe not only for false results, obviously, but also for failure to replicate. So the main cause of the replicability crisis is the chancy behavior of small samples producing noisy data. Next slide. Gellman proposes to address these problems by appealing to Bayesian inference, an approach in which data are combined with prior information. In this case, the prior expectation that newly studied effects tend to be small, which leads us to downwardly adjust large estimated effects in light of the high probability that they could be coming largely from noise. Next slide.
Another minute or so, Barbara?
Yeah, I'm finished. I have the questions now. So the next slide again. So my questions are, is there an opportunity to accommodate Gellman's proposal in your approach, the proposal to use higher order evidence about these studies in order to bet hypotheses? More specifically, is it possible to model bets for noise? May we think of testing protocol in that sense? Can skeptic make money by betting against too precise hypotheses? How? I mean here, that more entropic probability distributions might not multiply the risk money as much as more precise bets. Hence, the effect size and the noise might cancel out each other in some sense. Next slide. This is my last question, and then I have just some suggestions. One explanation for the reproducibility crisis is that noise is strategically exploited in order to sample to a foregone conclusion. That is, one selects and discloses evidence opportunistically in a pragmatic rather than merely epistemic sense. One way to do this is precisely to pretend to have stopped earlier than one actually did. This is something that also David was mentioning. How can your approach cope with this sort of phenomena? Next slide and last slide. A more practical issue. How can we make the entire framework more palatable to doctors or scientists more generally? I work in a medical faculty and I can see that the average student is rather disinclined to abstract theorizing and rather prone to ask for easy tools to go on with their differential diagnosis. So to yes, no questions. I suggest that we need to contextualize your framework in the context of information theory, not because it is about information theory, but because you use information theory to quantify and track this distance between probability distributions. If we don't want doctors to jump from an apparatus they use without understanding it, standard hypothesis testing, to another one they can understand even less. Thank you to the audience and thanks to Glenn. Thank you very much.
Thank you very much, Barbara. So we now move on to Aditya Ramdas from Carnegie Mellon University. Again, I can see.
All right. Hi, everyone. Thank you for the opportunity to discuss Glenn's paper. My discussion will be about other statistical arguments for employing betting scores, or as I'll also call them, e-values. Now, I personally vibe very strongly with Glenn's math and philosophy, but my question is, what if someone does not? And my aim over here in this discussion is to provide other reasons why one might be interested in e-values or betting scores. And it turns out that I've been working on this area for a long time, but I didn't know I was working on betting. I was working on martingales and sequential estimation and things of that kind. But when I read Glenn's paper, I was like, oh, I'm working on betting. That's amazing. So now in my work, we have tried to point out other orthogonal benefits. And so these are 4 of them, which I'll go through one by one. So just to get the notation clear for everyone, I'm going to, when we talk about the batch setting, I'm going to, an e-value or a betting score or a bet, I'm still getting used to the notation that Glenn and Vladimir Vovk and others are trying to introduce. It's just a non-negative random variable with expectation at most 1 under the null. In the sequential setting, it's a sequence of non-negative random variables such that at any stopping time, the expected value is at most 1 for any element of the null. Now, my work has mostly been about composite null hypotheses and non-parametric nulls. So that's going to be the flavor of things that I will discuss today. So the first advantage, which I think has not been appreciated as much in the discussion so far, is that the use of betting scores or e-values provides what's called dimension agnostic inference. So what does that mean? So we often rely on Wilks' theorem, which is something like the log likelihood ratio is asymptotically chi-square distributed. This only holds in certain regimes of the dimensionality P and the sample size N. And most classically, the dimension is fixed, the sample size is going to infinity. But modern high dimensional statistics has been asking, oh, well, what if P and N are both going to infinity, and how does the likelihood ratio behave in that setting, and so on. And it gets quite subtle. Now, when you have a data set of 1,000 data points in 500 dimensions, what do you assume about this dimension and sample size? So what I call dimension agnostic inference is a method that doesn't care about how P and N scale. You just have one data set, you have to make inference. And so it turns out that the mixture likelihood ratio, this is well known, but it's an e-value. But it's an e-value for any, or it's a betting score. It's for any P and N, for any dimensionality and any sample size. The mixture likelihood ratio is a score. And non-parametric generalizations of this idea exist. So this is well appreciated from Wald and Robbins and so on. But more recently, we've been able to extend this idea to settings where your underlying hypothesis or the quantity you're trying to estimate, you only know non-parametric things about it. For example, the distribution is bounded, or the distribution is symmetric, or things of that style. And there are extensions of these ideas to Banach spaces and matrices and so on. So if you like the idea of dimension agnostic inference, you can check out this recently published paper of ours. The second idea is about irregular models. And again, this is a setting of composite nulls. Now, Wilkes' theorem usually only holds for quote unquote regular models. And regular models, there's many ways of thinking about it. One way is, some kind of second order Taylor expansion. The Fisher information matrix is invertible, and, the Taylor expansion, there's asymptotic normality, things of that kind. And Wilkes' theorem of asymptotic chi-square distributions for likelihood ratios, it only holds for regular models, but there's plenty of irregular models. And the typical setting is latent variable models tend to be irregular models. And the asymptotic distribution of the likelihood ratio is typically unknown. So you can't form p-values, even if you wanted to. The bootstrap is also not known to work in such cases. One simple example from recent exciting literature has been testing whether a distribution is log concave or not. The likelihood ratio, the limiting distribution, is unknown. However, you can form an e-value or a bet, or a betting score. The split likelihood ratio statistic is an e-value whenever maximum likelihood estimation is tractable. So here what we do is we split the data into two halves, D1 and D0, calculate the maximum, for simplicity, maximum likelihood estimator on D1, calculate the maximum likelihood estimator on D0, but D1 for the alternative, D0 for the null, and then calculate this likelihood ratio only on D0. And it's a very simple argument to show that in any dimensionality, in any sample size, in any irregular model, this split likelihood ratio statistic is a valid e-value or betting score. And it allows you to do inference in composite, non-parametric nulls.
Just one more minute, I'm afraid.
No problem.
So choose carefully.
Yep. The third one is about sequential inference, which is where I've worked the most. And here, for point null hypotheses, all admissible e-values are actually martingales. But if you're interested in composite settings, admissible e-values need not be martingales, but they must combine point null martingales in some way. And if this is a recent work on arXiv, if you're interested, where we give examples of this, where the difference between a joint martingale, a composite martingale, and pointwise martingales is made. And the last example I'll give is about multiple hypothesis testing. Now, in science, you have k hypotheses. We have recently developed a generalization of the Benjamini-Hochberg procedure for p-values to apply instead for e-values or betting scores. And the main takeaway message, which is remarkable, is that the EBH procedure controls the false discovery rate under arbitrary dependence between the e-values. This is not known. This is known to not be true for p-values. There's a log correction you have to be that has to be made. And so again, if you're interested in FDR control with e-values, then again, check out our recent work. We were supposed to, this is my last slide, we were supposed to have a workshop at Eindhoven a few months ago on this topic. We call it Safe Anytime Valid Inference. Peter was one of my co-organizers, and many of the discussed, and I mean, actually Glenn was also supposed to be one of the speakers, and Vladimir Vovk as well. Got canceled because of COVID. I hope it happens next year, and I hope to see all of you there as well.
Thank you. You packed a lot in. That brings us very neatly on to Peter Grunwald from CWI in the Netherlands.
Okay, can people hear me?
Yeah.
Okay, could you put up my slides, please? I think you have them. Okay, so thank you for allowing me to speak here. Next slide, please. Right, so we've already heard about reproducibility, of course, and I would like to add a little bit to that. So at this point, we know, of course, that there are many people around the world investigating things related to the corona virus. And just to give you some idea, I was wondering, maybe people can make a guess in the chat. How many randomized clinical trials do you think are right now underway to investigate whether hydroxychloroquine, which I'm sure you've heard about, whether that really works? Just give some guess.
30.
30, okay, I see 30. Okay, next slide, please. Next slide. The answer is 156 and counting. Now, of course, some of these will be significant and some won't. And many of these have been started because previous ones gave hopeful interim results. So they are not independent. So how should we combine these? Very unclear. In the end, we will have a lot of research waste. That's how it's called officially. A lot of money will have been spent on things which we don't really know what they say. So this, I think, is a typical thing where we, so a typical application where we should use betting scores. And actually, well, we are not working on hydroxychloroquine, but together with my PhD student, Judith ter Schuure, I am actually now really trying to apply betting scores and meta-analysis. So our paper on that called All-in Meta-Analysis will appear hopefully a few weeks from now. Next slide. And so this was the slide where I was going to slightly criticize Glenn because I was going to say, well, why didn't you mention Ville's inequality in your paper? Actually, he didn't mention it in his paper, but he did mention it in the talk. So now I really have to say that I agree 200% with Glenn on everything. The reason I wanted to stress it that I think that gambling alone may not convince people. You also do want a kind of error control because, well, that's just what people want, and it's obviously a good thing. And so I wanted to say that with Ville's inequality, in principle, for example, if the null would really be true in all these 156 studies, then we would very likely not find a significant result if we would just multiply all the betting scores. So it might really work also in a type 1 error sense. And that means that not just likelihoodists, but also people with a Nymanian philosophy could be happy with betting scores, I think. Next slide. So that leaves the third group, of course, the Bayesians. And that's another thing which was not mentioned by Glenn. There's, of course, a very close link to Bayesian inference here. And as it's very long been known, basically already in the 60s, if the null hypothesis is simple, so you test a simple null against a composite alternative, then every base factor which puts the null in the denominator is also a betting score. That follows directly from Glenn's arguments. So you would think, okay, Bayesians think this is compatible with what they're doing, but actually it's more complicated than that, because for composite nulls, most base factors are actually not betting scores in Shafer's sense. And I write not because some people dispute this, but it's really true, unfortunately, that as a Bayesian, you can only guarantee a bet. So it has a betting score has to have an expectation bounded by 1. You can only guarantee that in expectation over the prior, whereas Glenn would like it to hold for all distributions in the null hypothesis. So if the null is composite, in general, a base factor does not give you a betting score. However, and I apologize for doing advertisement here, we recently showed that actually there is a connection after all, and it's really nice. So if you're a Bayesian, you give me an arbitrary prior on the composite hypothesis H1, the alternative, then I can construct a prior on H0 for you such that the resulting base factor is a valid betting score in Glenn Shafer's sense. Next slide, please. So it works as follows. You give me an arbitrary prior over H1, the alternative hypothesis.
Just a minute or so to get this across.
Sorry?
About 1 minute left.
Okay, that's fine. So what I do is I take the projection of the base marginal distribution with the prior W1 on the set of marginal distributions. So for every possible prior on H0 on the null hypothesis, this gives me a closest point, and I do the projection in KL divergence. And then I take the prior, which I get this way. I take that as a basis for a base factor. So I have marginal according to the prior given to me divided by the marginal which I constructed for the null model. And then we can show that this gives you a valid betting score in Shafer sense. And it's in some sense also the optimal one. So it grows the fastest in the log sense that Shafer talked about. So next slide, please. So you can generalize this also again beyond Bayes. I won't go into that here, but next slide, please. This is the final slide. So what's really cool about this is that this gives you a way for arbitrary, essentially composite nulls. You can create bets which are in a sense optimal, and you get very nice things out of it. For example, if we want to do the t-test, which is of course has a composite null, you don't know the variance, you get the base factor with the right higher prior. But for the 2x2 test, you get a base factor which is new. We use priors that nobody has used before. So we can do this and keep playing this game. And the one thing I wanted to stress is that communication is great, but there's more to these betting scores. I think they have a great future. Thank you.
Thank you very much, Peter. Right, from the Netherlands to Harvard. So we've got Xiaoli Meng. Over to you.
Thank you all. Can you also show my slides?
There you go.
Thank you. Like many of you, that I'm a great admirer of Glenn, and open his papers to me is a very unique experience. It's like open a well-aged bottle of wine, but then you will find some very fresh new flavors that others would not expect. And but I hope that I won't ruin Glenn's wonderful bottle of wine by adding a little bit of Bayesian flavor. And in fact, that probably contradict what Peter just said. But let's see. Good, next slide. So what Glenn did is a wonderful thing is to construct an implied alternative by just looking at the betting score, and as he showed in that in the paper. Next. Right, and so by doing so, you basically said, whatever the test scores or betting score you use, that's the same as doing like a ratio test against that particular Q. And so the idea, I think, quite a few speakers already talk about what happens if you have a composite, hypothesis. Next. And so suppose you actually, this Py is represent a composite null if indexed by theta, then by Glenn's construction, you actually have a composite alternative. And there's a question about what do I do with theta? Now here is a simple, next, here is a simple equation that may be very well known to some and may not be known to others. And basically you can show that very easily, it's an important sampling argument, that if you look at the posterior mean of and the denominator of the like ratio, that gives you the base factor. So in a way, you can directly interpret that what Glenn did in the Bayes fashion as well. It's simply a ratio of the base factor. So I need to understand what Peter just said about base factor do not have interpretation as a betting score. There is a caveat here for Glenn's construction that you need to require this S. Next, please. Require this S to be first order ancillary, basically saying its expectation is the one regardless of what the theta is. But that equality in red itself does not require the condition. So all I'm saying is that you can easily adding a Bayesian flavor to what Glenn just did. Next slide, please. So how did I notice that this equation was really, I was working on something called test informations. And because we know that if for an estimator, you give a model, a parametric, or otherwise you have a primary raw bound and official information to estimate its information. But what if, next please, what if you only have, only given a test statistic and a null model? How do you measure the information in this test? In this test, and I will say why in a second. Next, please. And it turned out that what you can do, this is a different from Glenn's construction, was you can also create a local alternative by exponential tilting. And the difference is that from this construction, what happened is instead of the likelihood ratio test, next please, instead of the likelihood ratio test is what's given, it's a log likelihood ratio test is what you get, is to start with. So the difference is taking log or not. But that actually turned out to lead to all the other things Glenn was talking about. You need to maximize over the log, not on the original one. And next, please. This was a work I did with Dan Nicolai and Augie Kahn, and in the content of the genetic studies, because Augie was working for decogenetics. He wants to know whether the blood sample he has enough information. Should he collect more blood samples or putting more markers in the existing blood sample? So it's information to determine whether you need to collect more data or not. And it turned out that's the way he construct these local alternatives in order to proceed. Next, please. And a former student of mine, we are currently sort of generalize this whole scheme into the measure information in this with only given a test. The reason I mentioned this is not only just this construction. Yes, next slide, please. And there's a powerful identity I call the EM extended EM identity. Essentially, is a generalized version of Glenn's Gibbs inequality. You will see the difference between them is exactly the KL distance, but this extension you will see there's theta 1, theta 2, but you average over of different theta. Here, YCOM is complete data, Y observed is observed data. Next, please. And so by choosing theta equal to theta 1, you get the Gibbs equality. Theta to theta 2, you get the reversed. But the point is that in our work that we use this inequality for many things. I believe it's also quite connected to what some of the inequalities Glenn was doing. Next, that will be last slide. Next, please. Yeah, go ahead. Next, please. And I want to remind everyone that there is a wonderful CR low bound, not the Kramer-Rao low bound. By the way, it's CR Rao's 100th birthday tomorrow. There's a celebration goes on. It's coincidence. And but this is the one. Next, please. This is the one probably is mostly forgotten. Is essentially statistical Heinz sort of insulting principle, basically saying the variance of estimator and the variance of likely ratio, the product of them has bounded below. This is a generalization of the CR Rao bound. Next, please. And
can I ask you to finish? Because
yes, please. Yes, I will. Yeah, and it's a Chapman-Robertson bound. The whole point is next, please. This last line. The whole point is that what Glenn said about this equality, about the variance of like ratio. The variance of like ratio is really a bounce. 1 over variance of like is a bounce on the information, very much like Fisher information, but it's a more generalized version. Next, please. And then the start. And basically, so this gives the Glenn's interpretation that the more variability in the likely ratio, that the higher the expectation of the S, which will give you more evidence against null hypothesis. So thank you very much.
thank you very much indeed, and sorry to rush you on that, but we're getting quite fairly tight for time, and I want to let the rest talk. So Arthur Paul Pedersen from the City University of New York.
Hi. Let's see here. This will suffice, I guess. See that? First, I'd like to thank Professor Shafer for his excellent summary of his discussion paper, and to all the organizers, of course, for putting together what has thus far been, an excellent discussion, an excellent meeting. And I'd like to congratulate Professor Shafer on a first-rate paper, and I look forward to seeing more of the developments over the next several years. I don't think you're done yet, although you indicated as much in Q&A that I read before the meeting today. I'd just like to make a few remarks this early afternoon in New York City. So Professor Shafer insists that using p-values for reporting statistical evidence is just too complicated, right, for effective communication to a wide audience. I mean, this is verbatim, right? Instead, the proposal advanced in the paper and outlined here today, right, very briefly, I'd say, betting by testing is, as Professor Shafer suggests, superior, not least in part because it is simpler, right, or whatever, for effectively communicating to a wide audience. I mean, what that means, right, is the question. And this has been raised by Frank Coolen and other commentators here today. But I'm going to press on that a little bit. I mean, despite your suggestive remarks. I mean, I'd have to say that you failed to lay out decisive or compelling reasons, right? I mean, for accepting what I take to be, you know, a chief selling point, right, in your advertisement for what you're doing, right? I mean, that's important, right? So, you know, what's the deal, right? Relatedly, and you know, in the spirit of, you know, open discussion or something like that, I asked Professor Shafer to clarify the content of his contention and the standards by which it is to be evaluated. You know, that is, what are the terms of the debate on this question? And by what criteria am I to evaluate any claims? I mean, I think this is really important. I mean, that everyone here is that you has allowed you to get away with it today is telling of how much everyone respects you. And that's my slide deck. Thank you.
Thank you very much indeed, and very nice timing. Right, as I said, we have got some written contributions that if we'd had longer, we would be taking, but I really do want to give Glenn a brief right of reply, reminding him that he'll have much longer in the journal, by which time he'll have seen these written contributions, other written contributions that exist, and indeed more written contributions that may well have been stimulated. So Glenn, perhaps 6 or 7 minutes, and then I'll wrap it up.
Thank you very much. I'm very honored by these comments and this consideration. I think I have so little time that I'd like to emphasize my thanks to everyone. I want to especially thank Phillip Dawid, who's been pivotal in the development of this whole viewpoint. In fact, some of his comments, if I had more time, I would remind him that he's the lead author on a paper that answers one of his questions. I also, of course, really want to thank Vladimir Vovk, who's worked with me on related ideas for 25 years. Peter Grunwald was really the inspiration for writing this paper. Conversations with him over a year ago were, I think, probably December 2018, if I remember correctly, were what led to the paper. So I think a lot of his ideas are somewhere in there. I appreciate Frank Coolen's comments, of course. His work on imprecise probabilities were also very important. And I'm most of all, I'm grateful to the younger people who are working on these ideas and related ideas, who really make me feel that you know, these ideas have a future. Not that some of the people I already mentioned aren't young, but there are others that are obviously very vigorously at work here. I'm also very impressed by, well, I'm just very impressed by some of the work. I think Phil is right to doubt whether statisticians and mathematicians are going to buy into this. Professor Hennig's comments at I think our last speaker is an illustration of their reluctance. I'm more positive not only by the public, but also about other scientists. Some of Judith Tershur, Peter Grunwald's collaborator on some of the practical work, has reported considerable enthusiasm from epidemiologists. And this point of view, they are finding the betting simpler. I think when you look at the history of probability theory and you ask, well, why is an idea betting? Everybody knew about betting before they knew about mathematical probability. And mathematical probability is about betting. That's where it comes from. If you didn't have betting, if it wasn't about betting, you'd have different rules. Early in my career, of course, I became known for proposals for combining evidence that didn't follow the rules of probability. Why do we have these rules? Because they're rules for betting. But if you look at the history, you see that James Bernoulli was already working very hard to suppress. He took Huygens' pamphlet on games of chance and tried to squeeze the betting out of it. I said, oh no, we don't justify these rules by betting arguments. We justify them because, oh, we know things are equally likely or something. Very sort of actually.
Asked him what he was going to charge me for installing, and he said £100.
Somebody else
I think someone else is speaking, but
Good, right.
so I think there are, if you think about what's happened, I think you would have to conclude that there's been a very serious effort to suppress thinking about the betting interpretation, the betting foundation for probability theory. And this has been done so effectively, not just recently, but for 300 years. There's obviously very good reasons for it. And Christian mentioned some of them, the moral objections to betting. I think for scientists, what's been so fundamental is that we wanted to make probability something objective. And now we're going, this other direction with the Bayesian subjectivity, that everything is about it is subjective. I think, when you look at the choice of bets, that's a very subjective element. And I think it may help us understand philosophically what really is subjective about our understanding of objective probability. It's because we have to, the objective probability is really a resistance to bets, but that only comes out when there's somebody to choose the bets, to choose how to bet against the probabilities. I really think that's all I have time to say. I look forward to the written versions of all these fascinating comments. And hope I can do justice to them. Thank you so much, everyone.
So thank you very much, Glenn. And the fact that I was having to manage the timing of the discussion so tightly and that we've not had some is a testament to how much discussion you've stimulated. So I think that's one of the best tributes that any red paper can have. So what I'd like to do, I've got one announcement to make afterwards, but can we wrap this up by using our technology again to really thank Glenn and all of the discussants for a really fascinating session. Right, so it just remains for me to announce that the next discussion meeting is on Gaussian differential privacy by Dong et al. And it'll be presented again in an online format. We begin to get some practice at these on the 16th of December 2020. And a final reminder that anybody that hasn't sent in a written discussion to this one but wants to, you've got some time, and it was in the chat as to how to do it. But wishing everyone on this side of the Atlantic a lovely evening, and those of you on the other side of the Atlantic a lovely afternoon, and anybody else in different time zones, whatever time of day it is for you. But thank you all very much indeed.